right. Um, Hello, everyone. Welcome to Terahertz Days. Everybody can hear me?
Yes, Mansour, we can hear you.
Yeah, I'm going to stop sharing and turn on my video. So first of all, welcome everyone to Terahertz Days. Just let me grab my presentation. So we are going to wait a couple of minutes more for our participants as they are joining right now. Well, there is difference between different time zones. And I warmly welcome Professor Angeliki Alexiou, who is here. Just before moving forward, just want to make sure that you and Dr. Gunesh already have access for sharing the screen and all the functionalities that is needed for this event. So starting from Dr. Gunesh, would you mind please let me know if you have access to sharing your screen?
Yes, Mansour, I can share my screen.
Thank you. Professor Alexiou.
Hello, I think I can, yes, I should be able to do that. So hello, everybody.
Hello.
Good day. Afternoon.
So thank you, Professor Alexiou, for confirmation. So I will show a couple of slides for you guys, and so just to confirm that this event is recording. So we didn't send this notification over the email, so just wanted to let everybody know that this event is being recorded. So let me share my screen. Yes. Terahertz Days. So this event has been initiated a couple of months ago, thanks to Dr. Gunesh, who gave us this opportunity to hold this serious technical workshop by inviting bright minds from the flagship research groups across the entire globe. And I hope everybody would get most of this event. And before starting the official talk and introduction of workshop chair and our speakers, I just wanted to ask everybody, please, if you have any questions, feel free to type in the chat box, and I will briefly let them know. We'll deliver to our workshop chair, Dr. Gunesh, and she will ask in the Q&A session. So in the meantime, that would be so nice of you if you please mute your microphone to avoid distractions and interruptions in the voice quality as well. Yes, workshop chair, this technical workshop chair, we have Dr. Gunesh with us. She is associate professor at Polytechnique de Montréal, adjunct research professor at Carleton University. She got bachelor's degree from Boğaziçi University, Istanbul, master and PhD from the University of Ottawa. And she is recipient of the Turkish Academy of Science Outstanding Young Scientist Award in 2019. And she is Marie Curie Fellow. Of course, there are a lot from Dr. Gunesh, but we just highlighted a couple of them. And I'm going to hand over microphone to Dr. Gunesh so she can introduce herself more precisely. And then we will hand over the workshop to Dr. Gunesh to introduce the workshop and our respective speaker. And then we all warm up and grab our chairs to stay and enjoy from this event. Thank you, Dr. Gunesh. I'm going to stop my screen, and you can share your screen.
Of course, Mansour, thank you for this organization. Could you please confirm if you can see my screen?
Yeah, we see this.
Perfect. Now, it's almost 12, so we are really punctual about the event, and I would like to welcome everybody for attending this first talk of the Terahertz Days. We are based in Montreal, and IEEE Young Professionals Montreal kindly organized this event, and you can see a nice picture from Montreal. So hopefully in the coming months, years, we'll have in-person meetings as well. And now this event is generously sponsored by Staracom, which is the Center for Systems, Technologies, Applications for Radio Frequency and Communication, which is a strategic regroupment based in Quebec. And we also have other technical sponsorships, including IEEE Terahertz Special Interest Group, Wireless World Research Forum, WWRF, and Ariadne Project. And so we are very excited about this first event of the Terahertz Days, and I am very happy that my good friend has accepted to give this very interesting first talk. Let me introduce myself. I am an associate professor at Polytechnique Montreal and also adjunct research professor at Caltech University. I was with Istanbul Technical University for more than 10 years, and I am a recent member at Polytechnique. And mostly I'm working on wireless communication systems. And I am the newest member of the Polygram Research Center. I would like to introduce Polygram before we start, because it's one of the well-equipped labs in North America, which was established in 1992 by Professor Bosisio. Professor Kevu is our current director, and there are many faculty members and a lot of very talented research team that has been conducting research in a number of fields, not only communications aspects, but not only the system modeling aspects, but also device aspects as well. So I am really happy to be a member of this team. And the Polygram has a lot of experience on millimeter wave and terahertz, and the activities on terahertz will be expanding towards the future. We wanted to organize these terahertz days because of this hidden potential of the terahertz bands for both communication and other applications. And to start this series, Professor Alexiou is one of the first prominent researchers that comes to mind, because he has been investigating a number of diverse aspects of the terahertz, especially from the system level. So Professor Alexiou, welcome to this talk, and I will introduce you briefly, although clearly Professor Alexiou has an impressive long resume. Currently, Professor Alexiou is a professor of broadband communication systems at the Department of Digital Systems, ICT School, University of Piraeus in Greece. She received her undergraduate degree in electrical and computer engineering from the National Technical University of Athens, and doctorate degree, PhD degree in electrical engineering from the Imperial College of Science, Technology and Medicine, University of London. Since 2009, she has been a faculty member, and she conducts research and teaches graduate and undergraduate courses on broadband communications and advanced wireless technologies. Prior to her switching back to academia, Professor Alexiou was with Bell Laboratories Wireless Research Lucent Technologies in UK, first as a member of the technical staff and later as a technical manager. She is the co-recipient of Bell Labs President's Gold Award in 2002 for contributions to Bell Labs Layered Spacetime project, which is the BLAST project, fundamental MIMO project, as we all know of. And she is the recipient of Central Bell Labs Teamwork Award in 2009 for role model teamwork and technical achievements in the IST fitness project. Professor Alexiou is the chair of the working group on radio communication technologies and the working group on high frequencies radio technologies of the Wireless World Research Forum. She is a member of IEEE ComSoc, and a number of committees. And also she is a core member of IEEE ComSoc's special interest group on terahertz communications. Her research interests clearly include 6th generation systems and the millimeter wave and terahertz extensions, reconfigurable intelligent surfaces, cooperation and coordination for ultra-advanced wireless networks, cellular architectures. She is the project coordinator of a number of, I think she has been serving actively in the European Union projects, and she is currently the coordinator of Horizon 2020 Terranova project, and she is the technical manager of Ariadne project, which is also our technical sponsor. So I would like to leave the floor to Professor Alexiou for interesting talk, and we will be asking the questions at the end and collecting them as Mansour kindly mentioned. So Professor Alexiou, thank you for being here, and we are looking forward to your talk.
Thank you very much. Thank you for the kind introduction and the invitation. It is my pleasure to be here. This is an excellent initiative, and I'm very happy that I'm actually, giving the first talk, and I'm looking forward to very interesting discussions and feedback and further talks like that. I think it is extremely important what you do to bring together the community. There are quite a few people working in this area, and I believe with so many challenges, it is definitely an excellent idea to exchange views and debate and discuss on certain things. So if shall we start? Do you want me to start sharing?
Yes, please.
Let me try. Can you see?
Yes, it's on the screen. Perfect.
Excellent. Okay, so what I wanted to with you is exactly what was also mentioned, that we believe it is important to address certain system level things. Obviously, over the last 5 or more years, there's been some progress in the field of terahertz communications, and several aspects from various angles, such as hardware, RF front-end, DSP, algorithms, etc. But I think, and I will try to discuss this in this talk today, I think the systemic aspects basically translate to the glue that will make all this work. So this is what we've been trying to do over the last 5 years or so, to address the directional terahertz communication system from these various angles that try to quantify all the challenges and the benefits, and also try to somehow combine two approaches: the bottom-up approach that recognizes the potential of the technologies, and the top-down approach that actually tries to understand the environment and the system concepts and the use cases where this type of potential could be better leveraged. The emphasis on the directional aspect is one of the things that we believe is a perfect match for the deployment of terahertz communication. So we will see that it is actually a requirement, especially because in such high frequencies there is the coverage issue, there is the range issue, but at the same time it is a potential just because We want to make the most out of the spatial dimension in terms of capacity, in terms of throughput, in terms of agility, in terms of localization potential, you name it. So there is a large number of scenarios where you can maybe search for all this benefit of the directional communication, direct communication, and I will try to explore this in this talk. So, having said that, the talk will try to use two system concepts, two, we believe, characteristic or representative system concepts on the deployment of the Terahertz wireless. The first one, that I name here pencil beamforming and optical network quality of experience, you could characterize it as evolutionary in the sense that it tries to look for the direct, let's say, extension of what we know today about broadband wireless with the aid of terahertz. And you will see what I mean when I present to you the scenarios. So based on this concept, I will just show you how we have studied. We started studying this concept maybe now more than 4 years ago. What was the main outcome, what angles and what aspects we have investigated, and I will show you some photos of the demos that came out of this effort. But the most important thing about investigating this system concept was that we managed to understand better, to get, you know, in the depth of understanding what Terahertz adoption would require. And this understanding led us to the second system concept, which you may consider as more revolutionary, what I call here beyond Shannon communications. And this one is actually trying to synthesize the benefits and the characteristics of terahertz in a way that offers intelligence in the network. Based on this second one, I'll just show you some results of some recent results of our work. So let me just start by saying that when one tries to understand what it means to introduce a new technology that would create the opportunity of a wireless frontier, I think there are three major milestones. There are three elements that you need in this synthesis. The first one is, first of all, you know, the technology. But the technology breakthrough integration comes with all the impairment, quantification, the real-time processing, reliability, and system integration challenges. The second ingredient is, of course, to work out the math. So we need a new framework that would help us design signals, waveforms, come up with metrics, and being able to assess performance both in fundamental terms and then in systemic terms. But the most important of these three ingredients is the third one, which is to synthesize the new system concept, take into account the specific use cases. So the specific characteristic of these use cases. What are the challenges, the requirements, and most importantly, the environment parameters that would greatly affect performance. So I think this trilogy, this kind of three main ingredients or milestone, I think they have been, you know, more or less help us structure our work over the last few years, and with these two system concepts that I talk about. So this is the first one, what I called evolutionary. This is a Terahertz system concept that tries to deliver optical network quality of experience. So the idea is, how can we make wireless behave and feel like optical? In doing that, the main aspect or asset we wanted to explore here was that of the co-design. Mainly in terms of co-design signals and protocols, so taking into account the specificities of the waveforms in order to optimize protocols at all layers, and the co-design of optical and terahertz. That means that the end-to-end optical wireless channel is now our basic element. So the idea is to propose the right baseband and the right RF design implications in order to be able to jointly optimize optical and wireless. And as I said before, the important thing is to work also the top-down approach and take into account specific use cases. So a natural direction to look when one wants to achieve this optical quality is, of course, what we call fiber extension. So we wanted to design fiber extenders, meaning that we want to cover areas where there is not enough fiber. And at the same time, we look towards the access and also took into account mobile wireless access and fixed wireless access, along with this multi-user indoor wireless access scenario. So you can recognize three main scenarios and two main use cases here. So the backhaul front haul being one, and the mobile and fixed wireless access being the second one. We wanted to capture that way the potential of terahertz in achieving very robust, high rate links that we believe could be a very important part, an integral part of the 6G network vision, and at the same time to address agility issues, adaptability issues, also on the access side of things. So you see here the group of potential applications one could consider under the backhaul fronthaul umbrella, and a group of potential applications that one could consider under the mobile and the fixed wireless umbrella. Of course, these are not the only ones. These are just examples. So what we did in Terra Nova, which is a European project that was completed back in March 2020, it lasted 3 years. What we did is to do the whole exercise. So we studied the propagation, the interesting propagation and path loss conditions that terahertz frequencies are actually, have to deal with, and extreme bandwidth issues and channel modeling issues. So one of the major outcomes of this work was to come up with a simplified channel model that is convenient for the studies and the analysis of the behavior. We also studied the impact of weather conditions, as you know, this important, and temperature in this type of frequency regimes. And we addressed the issue of distance-dependent bandwidth, that it is one of the major landmarks of terahertz links. We came up with algorithms that do adaptive modulation encoding, take into account also this dependence. The main, if you want, physical layer here, technology is what we call pencil beamforming. So beamforming with very sharp beams that, of course, would have to be, let's say, restarted from scratch, just because there are new issues of robustness here related to tracking, related to misalignment, and to blockage. So that was the main focus of the work at the physical layer and the map, was to understand what pencil beam based interface, what pencil beam initial access pencil beam MAC or multiple access or RRM would require. And in that respect, we studied the blockage problem, the problem of misalignment that was assessed both in analytical and in algorithmic terms, the problem of initial access with pencil beams, and also the requirement for network edge intelligence by means of caching in order to be able to address load balancing issues. Part of that work, on top of the analytical and the algorithms, the analytical sides and the algorithm, of course, was to build a demo. That was a collaboration of various partners, the partners who actually offered the demo hardware and they actually built it, were Fraunhofer, IAF, Fraunhofer HHI, and Intracom Telecom. So you see here the first demo that we had, the one that focused on the beamforming functionality, that was a 4x1, 1x4, both ways, antenna array that demonstrated the capability of steering the beam. It was not focusing on the wideband aspect of our studies. The focus here was mostly on the beamforming aspect. And the work was demonstrated in 2019 at the EUCNC, and it actually got a Best Paper Award. The second demo was the high capacity one. So this one focused on delivering very high rates in extreme bandwidths in an effort to show that we can have stability, as you see here on the bottom line. We can have robustness and reliability. It was also studied in terms of latency, and it was shown what we already expected, actually, that the major part of the latency is, of course, due to the processing, the Terahertz modem processing. The other aspect that was central in the study was the optical wireless integration, what I explained before, to show that the end-to-end, the combined channel, if it is properly designed, then it can offer a really stable, robust, and high-performing behavior. So you see here the various combinations, bit error rate in terms of the fiber terahertz, fiber terahertz, and terahertz fiber, and also the peak line that you see here is what I would call the phase conjugated situation, where you actually, as you see on the right-hand side, you compensate for chromatic dispersion, and you end up with this jointly end-to-end optimized fiber terahertz link. So the picture is actually from UCNC 2019 that was held in Valencia, and this is out there. The second part of the second demo was, and this particular one was not really planned. That came later as an additional activity of this work, was to also demonstrate that terahertz can work in the long range. And there were two experiments, two field trials. The first one was held in Freiburg in August 2019. You see here the link of 1 kilometer range. And the second one was in Berlin, right at the beginning of the pandemic, era, let's say, in March 2020, where it was demonstrated that you can achieve a terahertz link of 500 meters. So Terra Nova was successfully completed last year, and it was a great opportunity for us to be able to study all the aspects of terahertz communication systems and networks, both from the point of view of the hardware and how you are expected to build and address the various impairments of the algorithms, the analytical performance, and the protocols. But then towards the end of the project, we were wondering whether we have the full picture. So as you see on the left-hand side, we have managed to address a number of issues, a number of challenges, at least one by one, individually, that gave us a good understanding of the quantities, let's say, but not really of the qualities. What I mean by that is, if one can address individually the various particularities, does it mean that they have come up with a solution for how Terahertz communication can be the next wireless frontier? And does it mean that this is a qualifying system concept? Or does it remain a simple technology enabler? So what was made clear to us when we studied the various aspects was exactly that if you try to search for answers going bottom up, you probably get quite a few answers, but you're not sure if all of them make sense. So the idea of jointly trying to understand the top-down approach and translate the application and use cases, characteristics and specifications, and at the same time try to understand how fundamental principles and new technologies can address these specifications. I think that was a lesson that we learned when we were towards the end of Terranova, and that created a new, let's say, line of thought. So in this new line of thought, we try to see how can we make this new system concept intelligent. So intelligence, of course, can mean several things, but in terms of this trilogy of basic ingredients that I was talking before, intelligence is actually a way to introduce these three ingredients, but in a way that they affect each other. They are connected to each other. So this is what we did maybe 3 years ago when we were just trying to think what was coming next. And these three ingredients were offering the element of adaptability. So the element of being able to change the environment and impact the environment. And to do that, we needed a technology, and that was reconfigurable intelligent surfaces or materials or metasurfaces. They're known, with several names nowadays. So we needed a technology that was able to introduce this adaptability in an inherent fashion. We also needed a new framework that could describe this behavior, could describe the possibility to have also the environment as part of the design. And we also needed a tool that would take these two possibilities and introduce intelligence. And that was machine learning. So this thinking generated a new project and a new research collaboration that is called Ariadne. And there the idea of the system concept is this beyond Shannon intelligence. But of course, this can never work, as I said before, if you don't take into account the requirements and the specifications of a use case. So the step further that we took further from this evolutionary approach of Terranova was to try and see what are the really challenging environments where you expect to have terahertz communication systems. The fiber extender is the obvious. Fixed or mobile access probably is, the usual suspect. But what is the more important? So we try to see different environments that are gaining a lot of ground in beyond 5G, of the kinds of, for example, drone connectivity, V2X and V2V, backhaul, fronthaul, the indoor obstructed environment where you need to basically adapt to varying non-line of sight and obstructed conditions, etc. So in this study, we managed to isolate three main challenging, let's say, use cases. The first one is this backhaul, fronthaul. The second one is the indoor non-line of sight. And the third one is ad hoc or mobile connectivity and dynamic topology. So these are the three pillars of this work, as I said before, that are connected in a way that, you know, it is a circular, if you want, interaction or relation between the three. So if you take the reconfigurable intelligent surfaces, why do you want to use it in a Terahertz network? First of all, you want to do that because now, you know, you have the opportunity in these high frequencies to introduce surfaces with very large number of unit cells. So the programmability and adaptability of this new, let's say, technology can actually offer you very, very large number of degrees of freedom in these high frequencies. At the same time, you want to introduce the framework and the algorithms that take into account this programmability, take into account the importance of having in your signal processing, in your beamforming, etc., the possibility to basically design the channel, the wireless channel. And you need the framework that would use this, let's call it hardware and software, let's say, potential and capabilities to come up with offline and online optimization, and then as a next step, the online prediction. I believe I don't need to introduce that much RISs. They are famous by now. What I would like to only comment here is that RIS can be seen as an intelligent filter that can do what you see on the left and more. So it is basically a way to electromagnetically synthesize the response and your channel. That's why in this new framework, some people call it electromagnetic information theory. And that this is where the beyond Shannon communication actually comes in. Because in a Shannon optimization framework, what you want to do is you want to optimize, let's say, in a baseband fashion. But in a new framework where you have the ability to actually design, restructure, and create an adaptable wireless channel, it is, you add to the Shannon analysis, you add the electromagnetic theory aspect. So what you see here, if you want to look at a very simplistic, let's say, equation that illustrates what I just said, this is the composite channel. And you have the source, the RIS, and the destination. And what you want to do, on top of understanding, especially in the terahertz domain, HI and GI, you basically want to design a suitable RI, that it is also a programmable RI. So this is a schematic that shows you that in this new beyond channel framework, it is also the channel, the wireless propagation channel itself, that it is part of the design. And you could call this framework electromagnetic information theory framework. But then these two capabilities of the RISs and of this beyond channel framework would offer nothing if there was not, you know, the brains of that. And this comes from the AI framework, the AI tool. It is a long list of aspects, long list of models, algorithms, and optimization framework that can benefit from this, ranging from channel modeling, for example, profiling of the various weather effects like temperature and humidity, etc., beamforming design and tracking design, modeling the RIS behavior, and then one could use this tool for all the various network optimization problems, for example, resource allocation, placement, pairing, association of nodes, etc. So what I'm going to do in this last part, I would just like to share with you some recent results that we have worked on over the last year or so. And let me take this opportunity and tell you that, of course, there are other reports, technical reports, publications, etc., that you can find in the literature. And at the end of the talk, I'll just provide you a few links for easy access to this information. So let me spend the last maybe 10 minutes or so to share these results and findings. So I have selected 4 items, maybe these 4 that we're mostly interested in these days. The first one is about characterizing terahertz fading, because we know a lot about path loss, and there is a lot of work there. But in terms of the fading, I think still there are many gaps, knowledge gaps to really cover. Of course, this is justifiable in the sense that it is not easy to conduct measurements at that high frequency, so it is kind of expected. The second item I would like to talk about is 2 important impairments, the most important impairments of terahertz networking, that of misalignment and blockage. The third item is about beamforming efficiency, and I will use there the example of RIS to show how the combined beamforming and RIS design can actually affect and at the same time affect performance, and at the same time offer an optimization framework for these networks. And finally, I will just present a few elements that come from the machine learning and explain to you the approach that we want to take, and it is work in progress, this last one. So a first example about modeling the fading of terahertz wireless is this one that uses measurements that were conducted within our Ariadne consortium by Aalto University. So we were lucky enough to have real measurements on various, let's say, in various environments, and trying to capture issues of line of sight, non-line of sight, obstructed, non-obstructed, etc. 3 main examples here, 3 main measurement campaigns: shopping mall, airport, and the campus, their campus. So what we tried to do in our group was to try and understand, based on this measurement data, are there some maybe conclusions or some kind of indications as to how fading is behaving? So we came up with this fading exercise, tried to see, for example, if well-known distributions of the kinds of Rice and Nakagami and Alpha Mi can provide a nice fit. And we noticed that for the particular examples of the outdoor measurements, you need actually Alpha Mi to be able to match, to fit the behavior of the channels. And in most of the cases, Rice or Nakagami were not a good fit. Of course, let me explain that. measurements. We're still working on further data. We're lucky enough because Aalto, they still continuing their measurement campaigns. So the idea here is to follow a statistical, let's say, approach in understanding fading. Based on data, we try to see what are the distributions that would probably describe better this behavior. This would have a twofold value. The first one is because we will have a model, an analytical stochastic tool to use in our evaluations that we believe is backed, by real behavior. And the second value of this is that hopefully with getting more information on the stochastic models that hold in various cases, we would have a way to actually get into the anatomy of the terahertz fading and maybe, draw some conclusions there. The second example I want to use today is that of the impact of the antenna misalignment. So the idea here is that you have a source destination link and there is a degree of misalignment described here from by means of the variance sigma. And you compare this behavior for the various antenna gain figures that you see on the left-hand side. So what we can notice here is something that you probably expected to see, is that in the presence of misalignment, there is a certain antenna gain up to which transmission distance that you can reach increases, but there is a turning point in this behavior, an antenna gain beyond which this transmission distance drops. And this is because you basically, beyond this point, it is no more robust because of the presence of a misalignment to transmit that way. So beyond this point, misalignment actually monopolizes performance. What we're showing here, we tried several scenarios and several let's say options to try to address misalignment. Using relays is probably one way forward. So we compare on the right hand side the performance in terms of 1 and 2 relays, and we show that apparently yes, it is possible to improve by means of relays. But let me emphasize here that even in relays, there is the problem of misalignment, which is captured here, right? So you see a certain improvement that this redundancy by means of relay can offer you. The second very famous impairment of this high frequency is, of course, blockage. And you see a conceptual picture on the left-hand side that shows you an obstacle and how this affects the received, let's say, density, right? So the footprint of your beam is changed because of this obstacle here. Of course, one can argue that, well, an obstacle can actually reflect back and you can have other sources of received signal from the obstacle. But let's assume for this particular study that the obstacle actually blocks the same way that it is shown here in this picture. So what we did is we wanted to understand the statistics of blockage. We wanted to come up, with the PDF of blockage. I mean, how does it work? What does it mean to have a number of blockers in this space? So we realized something that was, again, not a surprise, that in most of the cases, the blockage model can be nicely represented by a binary process. So a Bernoulli distribution is probably more than enough. You see here on the right-hand side to describe the nature of the blockage. So it is a non-off, if you want, process. Why? Because in most of the cases, you have the sharp beams and you have the blockers that are probably larger in size than your beam width. So what we did is we tried to calculate this blocking probability in a couple of scenarios. First one is the scenario of the direct link. Second one is a scenario of a source RIS destination link. And the third one, it is a scenario that actually combines both the best of both worlds. What we call opportunistic connectivity is here, let's say, a protocol that always selects the best. So you see, as you would expect, that this blocking probability increases as this distance increases between the solid lines you see here represent a light blockage scenario of 10%, and the dotted lines represent a more severe, let's say, blockage scenario of 50%. So in that respect, what we wanted to understand, these were system simulations, we want to understand the severeness of blockage, we want to understand the impact and the interplay between blockage and placement of the nodes, and at the same time, as I will just mention, when I talk about machine learning, we wanted to collect statistics and data that would be directly used for the machine learning approach of avoiding blockage. The third example I want to use was that of the beamforming efficiency. So in this example, maybe you want to look at this picture of, there is a room, right? And there is an access point and a UE, so a transmitter, let's say, and the receiver, and there are RISs mounted on the wall. And there are, of course, blockers. So the idea is that the direct link is not possible. So you want to use RISs to guarantee the reliability of the connectivity here. So what we tried to study here was, if you want, the fundamental interplay between the various parameters, take into account, of course, the beam width, the antenna gain, the access point gain, which is basically your beamformer gain, and the distances from the access point to the RIS and from the RIS to the UE. So we want to understand the trade-offs and if you want the max and the minima, in a sense that what is the dependence of the various positions and how this can be, and this is what we did, described by deterministic equations that will be the metrics and the input to our optimization tools. So you see here on the left that one can actually observe two regions in this problem. For low antenna access point gains, but you see the gray area is actually the area of, let's say, of near field, whereas the white area beyond a certain access point gain, it is the area of the far field. So as you would expect, in this far field area, the received power drops because the actual access point gain becomes, if you want, of a smaller footprint, right? We went on and calculated this received power. Let's say that this is a good metric to understand how beamforming efficiency behaves in this case. So we investigate the received power for the various access point gains and for various distances. So in this top right graph, you see how the received power behaves when the distance of the UE from the RIS varies. And you see, as you expect, that this area of what I called before the near field does not change. So the behavior is identical because this distance obviously affects the area beyond this maximum. The other interesting conclusion is that in the case when the distance of the access point from the wrist is your variable, then what you see is that the maximum value of the received power does not change. But you see that it happens for, as you expect, for actually increasing, as you see here, for increasing distance, increasing access point gain values. So with this study, we wanted to create a framework of quantifying the trade-offs between access point gain and eventually beamforming footprint on the wrist, and the locations of the source and the destination, the access point and the UE. And this is what could be, as I said, used in an optimization that would actually look for the optimal placement of the nodes. And the third item, I don't have any results yet because our simulations are running at the moment. But this third item, I wanted study item that we are working hard to really understand is to take what I previously presented, take channel modeling, for example, take misalignment and blockage, take the beamforming efficiency and the RIS, and introduce this framework in a machine learning architecture. So you see here a schematic that it is mostly a cartography of the various, let's say, problems on the left or functionalities, the layers that they affect, and what we want to do with this optimization, meaning adaptation, rescheduling, or management. So this is mostly taxonomy of approaches. I don't want to spend time on that. It is as a reference figure for us to see what are the possibilities and what machine learning actually can offer for the various problems. And just to give you an example, at the MAC layer, where you want to implement blockage avoidance or optimization with respect to blockage, let's call it, channel allocation, and beamforming design, beam allocation, and power management, these are potential approaches that we understand it is worth investigating. So for the case of blockage, for example, one can use centralized machine learning or federated learning, as you see here in this schematic with the various brains that show you where the actual learning happens. But for the beamforming design, one may want to choose distributed learning because this is actually an optimization that runs in a distributed fashion locally. So we have at the moment this type of, let's say, interaction between the pillars that I showed you at the beginning, the three pillars. So we're working on, let's say, take the kernel characteristic, work out the math and the equations that describe the interplay of the various parameters, and introduce this synthesis into the machine learning, the various machine learning algorithms and tools. And that brings me to the conclusions. So we've been working on this in this area and on these problems that I try to list here over the last 4 or 5 years. So what we understood is that introduction of directional Terahertz communication would require the rethinking of wireless fundamentals beyond Shannon, and would also require the investigation of new powerful enablers of the kind of RIS and the use of tools, of optimization tools that include the element of learning. But to deliver the systems, the actual systems, there are many important angles and parameters that need to be all taken into account and actually countermeasured, if you want, including the transceiver design, the signaling and the algorithms, the joint design of the protocols that inherently support these characteristics. And these characteristics are not a simple add-on, and the offline and online optimization. So the smartness that we're targeting will have, if we want to deliver this directional terahertz communication system, will have to reside at various levels, let's say, both hardware and signaling and modeling, and also management and optimization. So this is mostly, I think, if I had to name one key success factor, I would definitely say that in order to be able, to be able to successfully introduce this powerful new technology, one will have to consider from the first, second, the particularities and the specifications and requirements of the scenarios that you want to take into account, and introduce these parameters, introduce these adaptability, let's say, factors at all levels. So this is, I guess, the conclusion. Just because, the title reads the role of these directional terahertz communication systems in 6G, I think it is a very significant role, especially because if you look at the discussions and the visions and all the wish list that concern 6G, one way or another, you can recognize that there are four main trends. Inclusion and global connectivity being one, and there definitely terahertz with fiber extended type of scenarios can offer a substantial contribution. Immersive connectivity is another important trend that is considered, very promising for 6G. And so immersion, this extreme rate, extreme agility, zero latency, etc. This is where probably terahertz also can be a very promising way to go. Intelligent connectivity by means of introducing, for example, many massive connections, data shower being one, or dynamic ad hoc mobile topology being another one, etc. So this type of intelligence, this is definitely a place where terahertz connections could play an important role. And finally, the Internet of Sensing. Okay, there I think it's obvious, especially if you consider the fact that when terahertz, the technologies, started becoming a trend, it was not the communication aspect that was the most, popular at that point. So really using terahertz in an integrated communication and sensing system is probably a very promising path. So with that, I would like to thank you. And thank you for giving me the opportunity to share my views. Thank you very much.
Thank you, Professor Alexiou. This was an excellent vision. It is at one, the potential is clear, and also the difficulties are also clear. I guess there are so many research problems that are open, and if we have young researchers in the or new researchers in the audience, I have spotted a number of PhD or master's projects in there. There are so many things that needs to be resolved. So we have 2 questions or 3 questions from the audience. I have a few questions myself, but I'll save them for the later. So Andil, I'll read the first one from Asil. What is the convenient channel model in terahertz communications? Recently, in many terahertz works, Saleh Valenzuela, a channel model is also commonly used as in millimeter wave with limited scattering. Apart from the increased path loss due to the higher carrier frequency, what is the difference between terahertz and millimeter wave channel models? Is that significant? Should we consider some other parameters in the model?
Right. So this is really a very interesting area, and there's been a lot of discussion. So 90% of the research effort in channel modeling actually focused on the path loss components, because this is where you have the most interesting and the most let's say dramatic impact, right? Including humidity, temperature, and other aspects. So what is, as you probably, and I think the question comes maybe from this end, many have followed the approach of really taking into account just the path loss and assuming that in such high frequencies you're fine, without really making any further assumption about fading, and say that this is all, a specular, 100% specular situation. But and we were very excited about this. We realized that in scenarios of, let's say, indoor or obstructed scenarios, there is also fading, and there, in many, for example, indoor scenarios, maybe some kind of rise model is also fine, but it seems that there is more to be investigated. So, of course, it all depends on the use case, but what I would say is that we need to further investigate, to watch this space about measurements. Maybe there are already some use cases where simple assumptions like Saleh Valenzuela and Rice and everything, maybe not, enough.
That's an interesting point. Now I will. I cannot resist but ask this question that actually I have in mind. You mentioned about the use cases. Do you see any use for terahertz bands in the emerging space networks, including satellites and possibly deep space communications?
There is now a lot of discussion there. Yes, it seems that the first indications are that this is a space to explore. I have to say I haven't really studied that. I haven't run any simulations to see the behavior, but I expect that we can specify cases where it can be worth considering, for sure.
Oh, that is very exciting.
Maybe you know better, right? You can answer that question better because you're working on this. So I really don't know. What are the indications? Are they encouraging?
From the lack of atmosphere seems promising. So, but I have this biased view. So towards terahertz, I am a big supporter. So I think it's all great that you also think that is promising. Now the next question is from Mansour, and it's about the implications of the use of AI. How will the data sets be collected for this AI-powered terahertz system management?
So we have in our studies two, let's say, sources of data, right? The first one is measured data of the kinds of the ones that I showed you in our little fitting exercise, but we have a substantial amount of measured data. And the second one is the data that we're going to produce. We are producing as we speak by means of system simulations. So these are the two, let's say, data banks that we're using. Now, the question is not how we select the data, but how we prepare the data. So we have some partners in the consortium that specialize on AI and machine learning, and they do a great job in helping us filter this data, preparing the data before they are input to the machine learning algorithm. So this is probably a quite critical, I expect, exercise.
It is that will probably provide a much wider insight about the data with this large data sets. Now I have two more questions that I know that we are running out of time, but I would like to ask these two questions as well. There is a question related to the intelligent surface example. Could you please comment on a practical example if we only have a small intelligent surface for scenarios in the range of hundreds of meters? It seems that the channel statistics, such as the singular value distribution, can only be influenced slightly, especially as the terahertz channels are the mostly line of sight channels. Wouldn't we need large surfaces to obtain significant gains?
Yeah, so large, what does it mean? I mean, in wavelengths, right? We need, that is true. So in these high frequencies, what I was trying to mention at the beginning is that we can actually build very large RISs with thousands of elements because we are, operating in such high frequencies and lambda is so small. But what I believe is the question is in terms of the misalignment, maybe. So if you have a surface that in meters is still relatively small, how do you solve the robustness to misalignment, to actually pointing the right direction? So this is a very important, and this is why we're studying aspect, especially if you think about a node being mobile, like the UE, because the access point RIS link is probably easier to manage, to deal with. So one element is that pointing and dealing with misalignment of the pointing towards the RIS. The other point that I didn't have the time to explain, although I should have, but in the references you can find a lot of information, is that we need to consider two different cases. So there is the case, what we call infinite RIS, and this means that the beam illuminates the RIS, and the RIS is large enough, to contain the whole beam. And what we call finite RIS, this means that actually the footprint of the beam is larger than the size of the RIS. Then the properties and the behavior completely changes in that. So the results that I showed you, although I didn't really mention that, but it's good that you asked because now I can explain it better. They are using the assumption of the infinite RIS. So it is important to consider these two cases. This is what we do in our studies. You can see more in the papers. And definitely the impact of these pointing errors, let's call it, is different in one or in the other case. But yes, this is a very important aspect actually. But as I said, I see that as a benefit. The fact that the lambda is so small, we can build, and this is part of Ariadne project to actually build and design and demonstrate an RIS, very large RISs with many unit cells.
Oh, that sounds very exciting. Thank you, Marco, for the question. And Angelica, we are looking forward to see the outcomes of the experimental work on the RISs on terahertz. And there is one final question. Is there any study investigating the electromagnetic lens usage for terahertz?
Not in this project, but I believe that there should be quite a lot of activities there, I'm sure. But we haven't really looked at this. It's not
excellent. I would like to. Oh, there are two more messages, but as a comment on the on the application of or the applications for terahertz waves in the high altitude platform stations as well. So this is a comment from Tahsin Akın. Overall, Andil, thank you very much for your time and this interesting talk. It was delightful. It was so much full of information. And I would also like to thank the audience for being being a valuable participant. And we will have the next speakers announced by the IEEE Young Professionals Montreal. And again, thank you for your time and participation. And we are looking forward to the next issue. À la prochaine. Bye.
Thank you very much. Thank you for inviting. I'm looking forward to more discussions then. Thank you, Mansour. Thank you, Guinness.
Thank
you, Mansour.
For thanking. So thank you, Prof. Alexiou, for your informative talk, and many thanks to Prof. Güneş for hosting this event as the chair. And a big thanks for all participants from all over the world, from different time zones. So it's fall here, probably it's hot in somewhere else. So that would be so nice of you to join us. And we very much look forward to see you again in the next sessions of the Terahertz days, and which will be announced soon. Once again, thanks to everyone for your presence, and I hope we would be able to see each other out of this COVID situation very soon, one day, hopefully. And until then, stay safe, everybody, and see you later.
Thank you very much. Bye.
Thank you. Bye.